Hey, flipped physics. How you doing? You know what this is? This is the last lecture for academic 2015-16 school year. Hope to get further down the book next year, but this is where we will end. So here we are at Refraction and Lenses, the second half of chapter 24. Let's go ahead and get started. Two kinds of lenses. There are converging lenses and diverging lenses. Lenses that gather light, where the light rays converge on a certain single point, and diverging lenses where light scatters. And so converging lenses tend to have convex surfaces where the surfaces of the lens go out in the middle and narrow at the end. Diverging lenses tend to be concave, where the middle of the lens is skinnier than the edges of the lens. Okay, quick pictures of these. Here is an example of a converging lens. Light rays coming in parallel to the axis will be focused at one point. They are all bent in and they strike at the focal point. Diverging lenses, light rays coming in parallel to the axis will be scattered out away and disperses the light, making the focal point actually behind the lens or in front of the lens, depending how you want to look at it. But the focal point is on the side that the light travels from, not on the side that the light travels to, like in the convex lens. Okay. Converging lenses are thicker in the middle, as you just saw, and that means that the light rays passing through slow down more in the middle, and so it bends the wavefront in towards the focal point. That's one way to think of it, is if you have a flat wall of light, when it hits the lens, the edges keep going a little bit faster and the middle slows down more, so it winds up cupping, and then as it continues on, that will close down to the focal point. Or you could consider that light is bent at the more extreme angles because of the more extreme curvature at the end of the lens, and they're bent inward, and that's what makes it focus. So if either of those mental pictures help you, good for you. Here are those two ways of thinking of convex lenses in pictures. So if you have a flat wavefront of light coming out the lens, the light in the middle is going to slow down more. The light on the edges is going to slow down, but slow down less because it goes through less of the glass. And so this light is now traveling this direction, and this light's traveling this direction, and this light, of course, is still going straight, and they're going to converge at the focus. So that's one way to think of these lenses working. The other way to think of it is if you have rays of light, this part of the surface of the lens is bent more than this part of the surface of the lens, so it refracts the light at a steeper angle, which is what pushes the light in towards the middle. Either of those could help you think of convex lenses and why they focus light at a focal point. Okay. Some similar terminology that exists here that also existed in mirrors is the concept of a focal point, a place where the light is focused or the image is focused. And we still have curved objects that have a center of curvature, and we still have real and virtual images. A real image is something that's on the other side of the lens. A virtual image is something is on the near side of the lens as the light is approaching the lens. Okay, distances from lenses to the image is a positive number. Distances from a lens to the object is a negative number. So just as we're measuring distance and displacement, we will talk about the lens itself is the reference point, that's 0. And then as it goes out to the image, then that will be a positive measurement, and a negative measurement going back towards the object that it's imaging. So think of it as like light just travels in the positive direction. It's the light of the object, or light bouncing off of the object going towards a lens. It's going to move in the positive direction. It'll be moving towards 0, the lens is 0, and then it'll keep moving positive towards the image that it eventually produces. Here's some images to help you with that. So if I have an object up here, and I want to know where is the image of this object going to be, the same rules that will apply with mirrors will apply here, where if you start off going parallel to the optical axis, and then it hits the lens. It will go from there through the focal point and then keep going. So the image of this object that is on a light ray going parallel to the image, to the optical axis, is going to turn and go through the focal point and then keep going. And then you could draw a line that goes through this focal point, hits the lens, and then winds up going parallel to the optical axis on the other side. And where those two lines converge is the image. Now, there's other lines you can draw too, but they're not as easy to find as if you start at the object, go through the focal point, and then go straight, and then start at the object, go straight, and then go through the focal point. You will find where those lines collide is where the new object's image will be. Okay, and this is shown offset. This is shown in line with the optical axis. So again, the lines all go parallel to the optical axis and then converge on the focal point. The distance from the focal point to the center of the lens is called the focal length. Okay, you could also, so there's the focal length there, and then object height and image height are some other things that we're going to look at in a minute. Just like in mirrors, you still have object height and image height. And then you have the distance from the object and the distance to the image. So these are all terms that will become meaningful as you play with images from lenses. All right, we had equations for calculating the distance of an object and the distance of its image with a mirror. And now we need to take into account the slight difference that a lens has, but it's the same idea. For a lens, the distance from the object and the distance to the image are inversely the two things that you add up to get the inverse of the focal distance. So 1 over the focal distance is the same as 1 over the distance to the object and 1 over the distance to the image. So the inverse of the object distance plus the inverse of the image distance gives you the inverse of the focal distance. You'll usually know this for a lens, and you'll know this, and so you can calculate this. That's usually how you're going to use this number. Okay. Magnification, height, and distance are basically the same concepts. If you have the ratio of the height of the image and the ratio of the height of the objects, you can use, ratio of the heights or the distances of the image to the object. Then you can calculate the magnification of the lens and know how much the lens is making your image look bigger or smaller, depending on how you're using the lens. Okay, so let's use a lens in an example problem here. A lens with a focal distance of 3 meters is used to look at an object 200 meters away. The object is 1.4 meters high. How high will its image be, and what's the resulting power of magnification? So first thing we need to do is use the lens equation to calculate the distance of the image. So 1 over the distance to the object is plus 1 over the distance to the image is 1 over the distance to the focal length. And I know the focal length is 3 meters. I know the image is 200 meters away, so I can plug those in. 1 over di is what I'm looking for. I'm going to subtract this, but first I'm going to turn them into decimals. 1 divided by 3 is 0.3 repeating. 1 divided by 200 is 0.005. I'm going to just subtract over here, right? 0.295. And then I need to take the inverse, 1 over di, and then take the inverse of this number, 1 divided by this. So if I take the inverse of 1 over di, I get di, and the inverse of 0.295, I get 3.389, yada, 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 meters. Okay? So that's how far away the image is going to be. Object is 200 meters away. The image is 3.389 meters away. Now, I need to figure out the magnification, and I need to figure out the height of the image. So the height of the image is what I'm looking for here. The height of the object, I know. The distance to the image, I just figured out, and the distance to the object was given to me. Notice the distance to the object is negative here because it's towards the object. That's negative direction. So negative 200, and here I have the distance to the image is positive 3.2787. How did that change? Interesting. And then the height of the height is what I'm looking for here, so I'm going to divide, and I get the resulting magnification on this side. Magnification equals this, and then I can use this ratio, this comparison here, and solve for HI. And so if I'm going to do that, I have to multiply both sides by 1.4, and I get negative 0.229509. And so the height of the image is this, and so the magnification is this. In other words, it's much smaller. The magnification is the image is much smaller than the object. Okay, and here's the height of the image. Negative because it's going downward. So the object would be positive, would be tall like this, and the image will be inverse, will be inverted, will be negative down. Okay, does that help you? The height of the image is downward and the magnification is negative, so it's a smaller object and it's inverted. And so that's something that we can use these equations to calculate. There you go. Divergent lenses, just a couple things to say about these. Convergent lenses and divergent lenses, you'll use the same equations and the same math. These lenses scatter light though, and so the image is always going to be virtual. Light is bent out more by the shape of the lens on the edges and spreads outwards. So as we've already seen once, the image is actually on the side of the light, not on the side that the light leaves after it's passed through the lens. And here you can see that. Here's flat wave fronts, and they hit this lens, and the light is slowed down less in the middle and more on the outside. So it kind of poochies out, and the light gets scattered. That's one way to think about it. The other one is, again, the angle of the glass here causes the light to move more radically on the edges in an outward direction than in the middle where it's mostly flat. So again, we have light being scattered, and that focal point is in front of the lens. So it's a virtual image, always a virtual image. Okay. All images are virtual. All images are erect and are smaller than the object. So you're going to get a small image that's standing upright and is in front of the lens. All images are on the same side of the lens as the object, and so they always have a negative focal length because, again, the lens is 0. Anything before the lens is a negative number. And then look over the lens rules on page 564 in your textbook, and it'll help you with some of these lens problems that we're going to be doing. Refraction lenses, scattering light lenses, dispersing lenses are used mostly for microscopes and cameras and telescopes. That's where we use these lenses mostly. And we tend to have them in pairs of lenses, compound lenses where there's one lens and then another. And so you'll see two lenses working together. We'll do some of that with the lab as well. And there's good reasons for that, because you can use one lens to create a particular type of image and then use a second lens to do something else with that image. So two lenses focusing an image can create great amounts of magnification, and that is useful for all of those devices that we just mentioned there. Okay, when you are doing lens problems with compound lenses, then what you need to keep in mind is that the object creates an image after the first lens, and then the second lens sees that image as the object. So you're just basically doing lens math twice. Do it once to create the first image, and then use that image as the object for the second lens, and see what happens to it after that. Okay, so do the math for lens 1 and then for lens 2. Here's just some examples of compound lenses. Here's a telescope. The first lens will take parallel light from a long ways away and focus it, and then the focal point here is picked up as the object for a second lens, which disperses the light into parallel lines so you can see it at your eyeball. So it's taking a large amount of light and making it something that is appropriate for you to see with your eye. This is just a picture of a very large telescope, and here's the eyepiece way down there that this guy will be using to look at some faraway, distant, cool thing. Cameras, 2 lenses, and they will focus an image through a mirror and a prism and back to your eye. And when this mirror moves out of the way, then the image that is being focused by these 2 lenses is picked up by the film in the old school, or by a light sensing chip that captures the image and makes a picture of it. And then again, compound microscopes. Here's one lens near your eyeball, and there's another lens here in front of the object you're looking at. There's actually another lens right here that focuses the light onto the specimen. So there's actually 3 or 4 lenses in a compound microscope, in a normal microscope that you would use. Okay, that's it. Lenses and refraction. God bless you. I'll see you tomorrow. Have a great day.